Electric field. Why electric field is there? Electric field is because of the charge particle. Now you know very well that there exists a charge particle, and you know very well that you can see in the screen this capital Q. Capital Q is the charge. Okay, and this charge creates magnetic field around surrounding the space. This capital Q charge creates surrounding electric field surrounding space. Now, because of this electric charge, how much will be the electric field that we have to find? If the charge is there, electric field lines will be there. If charge is there, electric field lines will be there. And because of this electric charge, how much is electric field in the surrounding space that we have to find? So how can we check the how much is electric field? How can we understand how much is electric field? So for that purpose we have taken a test charge. What is the test charge? Test charge is the another charge particle that we have brought in the electric field to test the electric field intensity of the particular charge. Our source charge is capital Q. You can see at the, this is the x-axis and y-axis, and at the origin we have a charge capital Q, and the charge of this capital Q, whatever is the Q coulomb or whatever is the coulomb the charge. Now you know very well that if charge is there, then electric field will be there because of this Q charge, and we have to find what will be the electric field because of this capital Q charge. So we have taken another charge particle Q naught. It is called as the test charge. Now the test charge we have brought, and now because of this capital Q, the force is exerted. Okay, so this test charge we have brought in electric field of this Q, and because of this, that the force is there in between the charge capital Q and Q naught charge particle, and this Q naught charge particle at a distance r from the source charge Q. We have to, we can find the Coulomb's law. We can find the force between these two charge particles by using Coulomb's law. We know very well that Coulomb's law simply, it is the 1 upon 4 pi epsilon naught magnitude of the charges between these two charge particles upon the distance between those two charge particles. The distance between these two charge particles is r. Therefore, the force between these two charges is equal to F equal to 1 upon 4 pi epsilon naught Q1 Q2 upon r square. We have to mention that what is the direction of this force by the unit vector, where r cap is the unit vector. R cap is giving the direction of unit vector. R cap here, it is giving the direction of unit vector. So the force between these two charges, origin source charge plus Q and Q naught charge particle, that F equal to 1 upon 4 pi epsilon naught Q capital Q small q naught upon the square of distance between them, that is r square, and the direction of these forces r cap. So as already we have mentioned that we have taken another charge, test charge, to test the electric field intensity of the source charge. So the charge, test charge having the charge 1 coulomb. The test charge having the charge 1 coulomb. Suppose the test charge having the charge 1 coulomb, so Q naught equal to 1 coulomb. We put the value of this 1 coulomb into the our equation, F equal to 1 upon 4 pi epsilon naught capital Q small q naught upon r square and the unit vector. We put the value of Q naught in this equation. We can find F is equal to 1 upon 4 pi epsilon naught capital Q upon r square into r cap. So this is our the electric field, that is because of the charge, source charge plus Q at point P, at point P, which is at a distance r from the source charge. Okay, now this is what the electric field because of this source charge plus Q. Okay, so the source charge plus Q, and this is nothing but not the force, this is the electric field intensity because of the source charge plus Q at point P, which is at a distance r from the source charge. Okay, so what is electric field? Electric field is nothing but the force, because force on a test charge from a particular charge. What is electric field? Electric field is nothing but the force on a test charge. On a test charge, what is the electric field? Electric field is nothing but the force due to test charge. Now we can find the mathematical definition of electric field, that is equal to 1 upon 4 pi epsilon naught capital Q upon R squared into R cap. Now you can see the difference between electric field and electric force. You know, the electric field is a force per unit charge. Electric field is a force upon test charge. Therefore, the unit of electric field intensity is Newton per Coulomb. Why? Because F is equal to Q naught times C. Q naught is the test charge. Or alternatively, we can write E is equal to F divided by Q naught. Now, E, electric field intensity, F is the force, Q naught is the test charge. Therefore, E, unit of E, it is a Newton per Coulomb. Newton per Coulomb. Unit of force is Newton, unit of charge is Coulomb. So, electric field intensity is nothing but the force on a test charge from a particular charge. Now, we can write this electric field intensity in terms of derivative and limit form. Limit Q naught approaches to 0, force upon Q naught charge, which is called as the test charge. From equation 5, we can see that 1 upon 4 pi epsilon naught, it is nothing but the constant. It is nothing but the constant. You know the value of 1 upon 4 pi epsilon naught. And the electric field intensity at a particular distance is constant. It never changes at the particular point. It changes with the distance. It depends on the distance of that point from the source charge. So if the distance increases, the electric field intensity will goes on decreasing. The value of electric field intensity is depend on the another point. It is depend on the that point, or it is in the space from the test charge. So if R is a very large, it's nearly about infinite distance. Then if we put the value of infinity, we will get the electric field intensity 0. Means at infinite distance, what will the electric field? It will be 0. We know very well that electric field intensity is because of the test charge. Suppose we have there is a vacuum and no charges, of course, no any particles there. There does not exist any electric field. There does not exist any electric field. We have a test, if we brought another charge, then electric field will be because of this charge. And if we brought another charge particle near to the source charge, then what will happen? The source charge will apply the force on this another test charge, whatever the charge is there. But in space, there may not be a single charge, there may be the many charges, many different charges will be there. So because of this, what will be the electric field? So we know very well that in this equation 5, if we put force is equal to mass times acceleration, as we know the Newton's second law of motion, force is equal to mass times acceleration. If we put here force is equal to mass times acceleration, then this acceleration will give us Q naught E upon M, because F is equal to your mass times acceleration. This Q naught is dividing, it will multiply here, and this mass will multiply, it will divide. So we will get acceleration is equal to charge naught multiplied by E divided by M, where Q naught is the test charge, E is the electric field intensity, M is the mass of the charge. So the acceleration, at what acceleration the test charge, either it will attract or repel, it will what will be its acceleration? It depends on the value of test charge, it depends on the electric field and mass of that charge particle. So there are many charges here, you can see there are many charges, and there are many charges, but because of the source charge means that we can call the another any charge particle Q, okay, and because of that electric fields will be in the surrounding space, this is called electric field. And this Q naught is the test charge, okay, and this whatever the distance between them. So we have already calculated what is the force between these two charge particle, and already we have calculated the electric field intensity at point P due to source charge Q. Now this electric field is surrounding in the space. Okay, so electric field is there because of the charge particle, and if there are
Excuse
many
me.
charge particles in the space
Excuse me,
like
sir.
q1, q2, q3 and q4, these are four charge particles
Excuse me, sir.
and they are at a
Sir,
distance of 1 rp, 2 rp, uh, r3p, r4p from the point p. Means this is the q1 is at a distance r1p from the point p, q2 is at a distance r2p from this point p. So the direction of electric field because of the q1 is in this direction, direction of q3 is in this direction, direction of q4 will be in this direction, direction of q2 is will be in this direction. So these all forces are applying force. Okay, q3 in this direction, q1 in this direction, q4 in this direction. So we can find the vector law of addition, and we can find the resultant electric field intensity, and that will be in the direction of E. So this E is giving the electric field intensity because of these all four charges. As you know very well that the superposition principle, the resultant electric field intensity is nothing but the addition of electric fields because of the different charges. You can see in this
excuse me.
figure
Excuse
there
me,
are four
sir.
charge particle q1, q2, q3, q4. Four charge
Excuse
particles
me,
are
sir.
there, and these four
अरे,
charge particles
sir.
q1, q2, q3,
Sanika,
q4
don't disturb.
are
Let
at a
sir complete.
distance of r1p, r2p, r3p and
गौरी
r4p
गौरीला आतमध्ये
from
घ्यायचंय.
point P. And
She's
we
waiting.
have to find what is the electric field
मी
intensity
नाही डिस्टर्ब करत.
because of these four charge particles. Resultant electric field intensity because of these four charge particles. We don't have to find the electric field intensity because of the particular charge like q1 or q2 or anyone. We will first find the electric field intensity at point P due to q1. What will be the electric field intensity at point P? Hello. बरं बरं ठीक आहे चालतं बघ. ओके, आवाज येतोय ना?
Yes, sir.
Okay, so we can find the what is electric field intensity at point P. What is the electric field intensity at point P due to q1 charge particle? It's simply, we know very well that it is a E1, and that is 1 upon 4 by epsilon naught q1 because of the charge particle q1 divided by r1p. It is a distance between the point P and q1. So we have written r1p squared, and the direction of unit vector r1p cap. R1p cap, it is a direction. This is electric field at point P due to charge particle q1. Now here is another charge particle q2, and we have to find what is the electric field at point P due to q2 charge particle. So we can simply again the same formula we will use 1 upon 4 pi epsilon naught. The charge due to q2 charge particle, we will write q2 upon the distance, square of the distance from the point P to the q2, that is r2p squared, and the direction of vector r2p cap. Similarly, for the E3 and E4, we know the value of electric field intensity at point P due to Q3 and Q4 charge particle. So we have written these four values of E1, E2, E3, E4. These are the electric field intensity at point P due to these four charge particles. Now, superposition principle says that what is the electric field intensity? Electric field intensity at point B due to the four charge particle is nothing but the addition of all the forces, addition of all the electric field intensity due to individual charge particles. So we can find the total electric field intensity at point P due to four charge particle is nothing but the addition of E1 plus E2 plus E3 plus A4. So suppose there are four charge particles, we will write the electric field intensity due to the four charge particles. So if there are n number of charge particles, we will just add all the electric field intensity at that particular point and whatever the electric field intensity of the individual charge particles. So we have the formula, and that we will put the values, and we can find the total electric field intensity at that particular point due to the individual charge particles. Now here we will take the common from each equation, because 1 upon 4 pi epsilon naught, it is a common in each value. So we will take it common, and we will get q1 upon r1p square, r1p cap in case of the second charge particle, r22 upon r2p squared, r2p cap. For the third, similarly, we have the different values for the electric field intensity, and we can write these values in terms of algebraic summation. As you know very well that we can put the values, and we can write in short these values in terms of the electric in terms of the algebraic summation sign, because 1 upon 4 pi epsilon is constant, and we can find the direction of this electric field intensity, resultant direction of electric field intensity due to the electric field generated by the individual charge particles. So this is also called as a superposition principle, and we can find E is equal to 1 upon 4 pi epsilon naught algebraic summation I goes from 1 to n if there are n number of charge particles. If there are 4 charge particles, we will write is Q is equal to I goes from 1 to 4, where Qi upon Rip squared Rip, where in case of I, you can put if the charge particle is 1, then 1. If charge particle is 2, you can put the Q2, and similarly you can put the different values. It depends on the how many charge particles are there and how much the electric field because of these different charge particles. So this is what you know very well, that if the charge particle is stable, stationary charge particles, because of that the electric force is there. But what will happen if charge will move? Okay, if charge particle is moving, then it generates, it creates the electromagnetic waves. Do you know this thing, that if charge particle in motion, which creates electromagnetic force, electric force as well as magnetic force. Stationary charge creates electric force, but if the charge is moving, it creates electric and magnetic force, and these two are perpendicular to one another, and which create the electromagnetic waves. Suppose the source charge Q is moving from the origin, and which will generate the electromagnetic waves. You can see in the case of the induction, okay, in this process, the electric field lines and due to the induction process. So this is called as the electric field intensity due to the different charge particles. Now the another subtopic, that is a continuous charge distribution. We already studied that at the origin we have a source charge with any charge particle. Okay, we don't know how much Coulomb it is, but we can find the electric field intensity because of this charge particle. Now suppose this is the three-dimensional geometry, x-axis, y-axis, and z-axis at O. Okay, and Q1, Q2, Q3, Q4, or like three charge particles are there, and these having position vector r1, r2, and r3. The position vector, you know very well that position vector, that position of that particle from the origin. So r1, r2, r3 are the position vectors of the charge particle q1, q2, q3. Now we have to find what is electric field at point P, and this P point, the electric field intensity you can see E1 in this direction, E2 in this direction, and E3 in this direction. So the field will apply, and the resultant electric field intensity you can see in the picture. This is called as electric field intensity. It is a resultant electric field intensity because of these four charge particles. You can see here the distance between this q1 charge particle r1p. Okay, so r1p is the distance between the point p and q1, and the r1p cap is the unit factor. In case of second charge particle also, r2p is the distance between the charge particle q2, and r2p cap is the unit factor. So just now we have used the superposition principle. We can also here use the superposition principle, which says that the electric field intensity at a particular point is nothing but the electric addition of all electric field intensity which is generated due to the individual charge particles. So E is equal to E1 plus E2 plus E3. Okay, we will put the values 1 upon 4 pi epsilon will be common outside the bracket, and we can put just value Q1 upon R1p square, R1p cap plus the value of electric field intensity to the second charge particle, that is Q2 upon R2p squared, R2p cap. So this is what the resultant electric field intensity, or we can say the total electric field intensity due to the individual charge particles, which is nothing but the addition of electric field intensity of all the charge particles. Now there is another subtopic that is called as continuous charge distribution. Continuous charge distribution. Continuous charge distribution. So there are three types. One is the line charge, second one is the sheet of charge, and third one is the volume charge. Sheet of charge is also called as the surface charge. Okay. So line charge, surface charge, and volume charge. Line charge, surface charge, and volume charge. So these are the very basic concept, that line charge, surface charge, and volume charge. You can understand this concept from the shape of these different objects. Line charge one dimension, surface charge two dimensional, and volume charge three dimensional. So in case of line charge, suppose a line is there and the charge is accumulated on that surface. You can see in picture that different charge particles are there. This plus charge is accumulated on the surface of this metal or whatever it is. Suppose the length of this charge rod or whatever it is a capital L, and we have taken the very small surface area, very small region having the charge plus Q, or we can say delta Q is a small charge, and the length of this small element is a delta L. This charge particle, the small length is a delta L, and it's having the charge delta Q. So we can find, we have a ratio of this small charge delta Q upon small length delta L. So we can find delta Q upon delta L. When the charges are not uniformly distributed, you can see picture is not uniformly distributed. It is uniformly distributed, not okay now, but here is they are uniformly distributed. But when they are not uniformly distributed, that time we can use the lambda is equal to delta Q upon delta L. Delta Q upon delta L. Delta Q upon delta L. Delta Q upon delta L is called as the line charge density. It is called as the line charge density when the charges are not uniformly distributed. If the charges are uniformly distributed, then lambda is equal to total charge on this line element, that is a Q upon total length capital L. So lambda is equal to Q upon capital L. So this is called as the line charge density. Now similarly, in case of the surface area, it is a two-dimensional, and the total charge on the sheet is capital Q, total area is capital A, and we have to find the surface charge density. Surface charge density, I am mentioning the density. Okay, so as you know very well, density is a mass per unit volume, mass per unit volume. So in case of here, it is a charge density, so we are using charge upon whatever the length element, area element, and volume element. Now this is a charge, or this is a sheet, and we have divided this sheet into equal parts, into different equal parts. And this very small region you can see here, this small region having the area delta A, and the charge accumulated in this small area is delta Q. So sigma giving us the surface charge density, that is delta Q upon delta A. But this delta Q upon delta A, when these charge particles are accumulated on the sheet, but they are non-uniformly distributed. If the charge particles are not uniformly distributed on the surface, then we can write the surface charge density is delta Q upon delta L. But in case of the charges are distributed uniformly, that time we can use the formula sigma is equal to Q upon A, that is total charge upon total area simply. So what is the sigma? Sigma is the surface charge density, and it is equal to charge per unit area. Sigma is the surface charge density and is equal to the charge per unit area. Now third one is the volume charge distribution. It's similarly to the line charge density and surface charge density. We have a three-dimensional object, or it is a three-dimensional space, a three-dimensional region, three-dimensional object, three-dimensional. In case of in three-dimensional object also, we have made a different small regions which are equally distributed. We having the same dimension, and if this very small region we have taken having the volume delta V, and charge in that small volume is delta Q, then rho is giving us the delta Q upon delta V, and this is called as the volume charge density. These are the small regions, okay, and these are the equal volumes and having the equal charge distributed. So if they are ununiformly distributed, not uniformly distributed, then rho is giving the delta Q upon delta V. But if these charges are uniformly distributed, then that time the volume charge density is given by the ratio of total charge upon total volume, that is Q upon V. So this is about the continuous charge distribution, line charge density, surface charge density, and volume charge density. You can see three-dimensional space XYZ axis. We have an object, okay, three-dimensional object, and its volume is delta V for the small region. It is having the charge delta Q for the small region. So we can find the volume charge density by taking ratio of the delta Q upon delta V. So that delta V is dividing, it will multiply to the rho. So we will get from this delta Q is equal to rho multiplied by delta V. We have a point P in the space, and which is at a distance of R from this point. It is another point from this. We can say the direction of electric field because of this will be delta E in this direction. You can see in the picture. So electric field at point P due to charge particle which is here, okay, due to this region at this point. So we can find simply, we have formula, we can find electric field intensity at point P due to this small length element, due to the small surface volume, due to this volume delta V, where the charge is delta Q. So we can find what is electric field intensity at point P due to this region, very small region, having the charge is delta Q and delta V. So we have formula delta E is equal to 1 upon 4 pi epsilon naught, which is the constant of proportionality. Delta Q is the charge upon the distance or the square of distance between point P to this region, this small element, which is the symbol R dash. So we can take the R dash square, and R dash cap is the unit vector in which direction the electric field is there. Now this is what the electric field intensity, very small electric field intensity at point P due to the very small region having the charge delta Q. So suppose as we know very well that if a surface contains the this type of very small volume delta V, there are numbers of these volumes of exist. Therefore we can find the density. This electric field is equal to 1 upon 4 pi epsilon naught. In case of delta Q, we can write rho delta V into these values. So you know very well that rho is equal to delta Q upon delta V. Therefore, delta Q is equal to rho multiplied by delta V. So we put this value in this equation, and we can find, okay. So we can take integration also. This is the value. You can see delta E is equal to 1 upon 4 pi epsilon naught rho delta V upon R dash square into R dash cap. Okay. This is the electric field because of this single point, a single or very small surface area, we can say unit volume, and the charge in the delta Q. But for the whole surface, we can just integrate this value delta E from point A to the B. It means that the whole value from one point to another. So total electric field inside this three-dimensional object is integration over A to the B and value of delta E. So this can be calculated. Now this was the about the electric field lines, and as you know very well that electric field intensity is because of the charge. Electric field intensity is because of the charge particle, and you know very well that the electric field is there because of the electric field lines. It is an imaginary line, we cannot see that line, but because of these electric field lines, the electric force is exerted on the another charge particle if we brought that another charge particle to the source charge. Suppose we have a charge particle plus q, and there is a point a, and this you can see the another charge particle a, which is at a distance of r from this charge particle q, and electric force will be there, of course. So we have the three charge particles from this source of charge q, and that a charge particle, b charge particle, c charge particle. So you can see, so there will be the electric field lines. These are the electric field lines, electric field lines. Okay, so electric field lines is there, isn't it? So the charge particle a, b, c will experience a force by electric field lines from the source charge q. How this ABC charge particle experience the force? Due to the electric field lines. Either it may be attractive force or repulsive force, and that can be observed by the electric field lines that is originated from this another charge particle. Now you may have a question that what type of electric field lines are there and how that electric field lines are originated. So there are different or n number of electric field lines is surrounding from the charge particle. If any charge particle is there, then there exist different numbers of the electric field lines is spread out into the surrounding surface area. You can see in the picture also. So these are the electric field lines. You can see. Okay, so we have to study about the electric field lines, and you can see, suppose this is a surface area a. Okay, you can see this. So these are the number of electric field lines that is passing through it. These are the field lines that is passing, and from b also there are different lines of electric field lines are passing. So a is the any surface area element or any surface through which the number of electric field lines are passing. From b also the number of electric field lines are passing. So here the concept comes related to what? The number of electric field lines passing through the area A, number of electric field lines passing through point B, and you can hear the compare between the electric field lines passing through point A and passing through point B. Of course, you will say that if we compare the number of electric field lines which are passing through point A and B, so number of electric field lines passing through A will be more compared with the number of electric field lines that is passing through point or between the or through the sheet B. So, and another reason is that the sheet A is near to the charge particle Q, so it will have the more or strong electric field compared with the sheet B, which is at a distance more than that of the sheet A. So the sheet A experiences the more electric field, stronger electric field compared with the sheet B. So this we can understand. Here is one concept called as the electric flux. Okay, so you can see, suppose you can imagine the shape of the cone. You can see, you know very well that the what the angle, simply two lines are there, and from these two lines whatever the angle is called a simple, you know, the angle. But if the cone is there and whatever the angle inside it, that is called as a three-dimensional angle. It is called as the solid angle. Okay, you can imagine this is a cone shape and this r is the radius. So this angle, okay, circular angle, you can see solid angle is called as delta omega. Delta omega is the solid angle. You can see this, okay, three-dimensional angle. So it is called as delta omega. So linear angle simply between the two lines, okay, two lines whatever the angle. But this is a angle, this is a three-dimensional angle delta omega. Now this upper side, you can see upper side of the cone, that is a surface area. You know the surface area of this. So surface area, this upper surface area of the cone is delta s, and the solid angle is delta omega, and r is the distance of, you can see, radius. So you can see here this delta omega is equal to delta s upon r square. This is a formula for the angle, solid angle, that is the upper surface area upon the radius. So delta s is equal to r square multiplied by delta omega from the equation first. So delta s is equal to r square multiplied by delta omega. So you can see there is a positive trace charge q and the electric field lines are there. So delta s, we can see delta s is equal to r square times delta omega. Again here the same concept we have to observe here. So plus q charge is there, so number of electric field lines will be there into the space, and suppose x is one point, one region, this much region, this much surface area, and y is here also, there is a surface area, this much surface area. So r x region is at a distance r1 from q, but y region is at a distance of r2 from the q. Now this delta omega is the solid angle. Now delta omega is equal to delta s, that is the surface area of this region x, upon r square. Okay, so delta s is equal to r square delta omega. For this x region, delta s or surface area is equal to r1 square, is the distance from this value x to the q, that is multiplied by delta omega. And delta s2 is what? Surface area of y region, is equal to r2 square, means this distance r2 square from the q into delta omega. What is E1? E1 is electric field. Electric field due to the number of lines, number of electric field lines divided by the surface area delta S1. So this we can find this n is the electric fields, number of electric field lines divided by delta S1. So we can put the value of delta S1, that is equal to R1 square delta omega. From this we will put here. In case of E2, electric field at point Y, okay, this region, it is equal to number of electric field lines, n is number of electric field lines divided by the surface area delta S2 at the region of Y, okay, this area, that is equal to n upon the value of delta S2 from here R2 square delta omega. Now we have E1, that is n upon R1 square omega delta omega, and the value of E2 is equal to n upon R2 square delta omega. We will take the ratio of this E1 and E2. What is E1? E1 is electric field at point X. E2, what is the E2? Electric field at point Y. So we can find the ratio of E1 and E2. The ratio E1 upon E2 is equal to n upon R1 square delta omega upon n upon R2 square delta omega. Cancel out the common terms, and the redistribution of R1 square and R2 square, we will get E1 upon E2 is equal to R2 squared upon R1 squared. So E1 upon E2 is ratio of electric field intensity between the region X and between the Y. You can see this is the region, okay, this much region of surface area X or surface area Y, this area, which is called delta S, and this is called as the delta S1. This is called as delta S1. Okay, this area, circular surface area delta S1, and this circular surface area delta S2. This ratio is depend on again the distance of that region from the source charge Q. So it is inversely proportional, and we can see if the distance is higher the distance or more the distance from that region from the source charge, less will be the electric field, because this square of the distance is the inversely proportional to the electric field, or electric field intensity is inversely proportional to the square of that region from the source charge from where electric field is generated. Now let's understand about the electric field lines. You know very well that electric field, suppose you can see positive test charge, another test charge particle minus q, we have a one charge particle plus q, another charge particle minus q, and we have these two charge particles. Suppose we have two positive charge, and then that means the electric field is generated, electric field lines is originated from positive charge particle, and this there is a repulsion between the positive. You can see in picture, this is giving the animation how the electric field lines are there, But if there are two charged particles, they are oppositely charged particle, then that time the electric field will be originated from the plus q charge. And you can see these are the electric field lines. These are the electric field lines that is originated from positive charge. Always remember, electric field lines is originated from the positive charge particle, and these lines, electric field lines, is ended at negative charge particle. There is no circular loop, because the positive charge, the electric field lines is originated, and that is the starting point of electric field lines, and that is passing in the surrounding space, you can see in picture, and these field lines are ended at the negative charge particle. Okay, so you can see this picture where the how the electric field lines are exist between the two charge particle if they are oppositely charged, like positive charge and negative charge. If we want to find the electric field intensity at any point, we just have to take the tangent to the any electric field line, which gives us the direction of electric field intensity. We want to find the direction of electric field intensity, we just have to take the tangent at the any electric field lines, which gives us the direction of electric field intensity. Now these electric field lines are imaginary, but these electric field lines are originated from the positive charge particle, and these charge particle get electric field lines that terminated at the negative charge particle. So this is the animation which gives us the actually how the electric field lines are exist between the two oppositely charged particles. We have two charge particle, and you can observe these electric field lines. As you know, the important fundamental property that electric field lines never intersect each other. Electric field lines do not intersect each other. Okay, whatever the electric field, suppose they will intersect, that time the direction of electric field will be different, and that is not possible. Hence the direction, hence the electric field lines never intersect each other. Now you can imagine here, you can see in the picture that if the more the charge, the electric flux will be more. It means that number of electric field lines will be more. Okay, you can see if the more charge exists, the more will be the electric field lines, and we can say the electric force will be there. More will be the electric force if the charge is more. Number of electric field lines will be more if the charge is more. Okay, so electric field lines, it depends on the how much is the charge exist. Okay, so uniform electric field lines are parallel, equidistant, and unidirectional. Okay, in case of uniform electric fields. Okay, so these uniform electric fields have a, these all electric field lines are parallel and they are equidistant. Okay, but in case of non-uniform electric fields, we can see the direction of electric field in the picture. Okay, so in this way, this the first part, that is two important things we have studied here. First one is the electric field. What is the electric field? How the electric field is related to the uh, electric force, and second one is the electric field lines. Okay, so these things we have studied here. Now the next second part is the electric flux. Okay, let's start about the electric flux. Okay, you can see in picture the water is flowing from right to left. We have a two channel, V1 and V2. The water is flowing from right to left, and that water is collected at a jar. You can see picture that V1 is the velocity of the water which are flowing through this channel V1, and V2 is the velocity of the water flowing through the channel V2. Okay, so this you can see. First, we will take this height of these two channel is same. So you can check the if the Q2 is less than Q1. What is the Q1? The water quantity of water accumulated from these two region. V1 is the velocity of the water. If that is the this V2, the channel V2 is tilted at the particular angle, the amount of water collected, you can see the flow of water will be more. In picture you can see the water collected Q3 and water collected Q2. The water collected at the Q3 and Q2 is depends on the channel or the region of channel. If that the channel is at a degree 90 degree, then the velocity of water you can observe, or in case of that channel it is a tilted at the particular angle, the water flowing through it will have the more velocity and the more cross sectional area. In case of the if it is a perpendicular, the region will be the or the area will be less. If it is a tilted, that time the region will be more surface area will be there. So in this experiment we have used, doing this experiment is the simply just showing that if the channel, okay, the water was flowing into the two channels, and we have one jar, from there we are collecting this water. Okay, suppose that channel is a vertical making 90-degree angle, that time the whatever the region of this rectangular shape through the water it is flowing. Okay, and we have collected the water. But if that channel is shifted, tilted with particular angle, means it's not a 90 degree, and it's shifted towards the left side, is a tilted, that time the more surface area will be there to pass the water through it, and the water accumulated in the jar will be more compared with the channel which we have used in the experiment to make it perpendicular to the flow of water. So whatever the amount of water that is collected in the jar, that is equal to the velocity of the water multiplied by the area of the channel. So again I am explaining, the amount of water collected in the jar is equal to the velocity of water multiplied by the area of the channel. This experiment is only giving information about the amount of water collected is depend on the velocity of water and the area through which water is flowing. So in case of this water collection, we will use the formula, the amount of water collected, it is equal to the velocity multiplied by the velocity of water multiplied by the area region through which water is flowing, and multiplied by the cos theta cosine angle. So the outward, it is the outward normal, and we can find the amount of water collected in the jar by using the VA cos theta formula simply. Now this value Q is equal to VA. It is a dot product because we know very well that V dot A is equal to VA cos theta. It is a dot product of VA. So V dot A is equal to VA cos theta. So we can write VA cos theta equal to V dot A. We can see in this experiment similarly in case of the water, suppose the electric field lines are there, and whatever that area we have shown the channel area, we have a particular region A or any particular region A sheet A through which electric field lines are passing. So if the electric field lines are passing through region A, then the electric flux is equal to the electric field intensity multiplied by the area A. Suppose we have an object and E1 is the electric field, the area of this region is AY, then the flux, electric flux can be calculated by using the electric field intensity multiplied by that surface area. The experiment is just giving the information about the amount of water collected depends on the two parameter. One is the velocity of the water and the surface area. More the surface area, the more will be the water collected. More will be the velocity, more will be the water collection in the jar. Similarly, in case of electric field, the same thing is there. If